December 14th, 2005. In the dark silence atop Proffit Mountain, sensors claimed the Taum Sauk reservoir was safe, yet 1 billion gallons of water stood poised above Missouri. Within minutes, automated trust, hidden design flaws, and overlooked warnings would erase entire landscapes. How could a dam designed to store energy become the force that destroyed whole cities? The answer begins with the risks nobody saw until the safeguards failed. Pumped storage plants like Taum Sauk are built to act as giant, reusable batteries for the power grid. Instead of storing electricity in chemical form, they use gravity and water. The idea is simple. When electricity is cheap and demand is low, usually at night, powerful pumps move water from a lower reservoir to a higher one perched on top of a mountain. That water waits there, holding stored energy as potential. When people wake up and turn on lights, or when factories ramp up during the day, electricity demand spikes. The plant responds by releasing the water back downhill through turbines, instantly generating power and feeding it into the grid. This cycle can happen every day, sometimes more than once. Unlike traditional dams, which are designed to hold back rivers for months or years, pumped storage facilities fill and empty their upper reservoirs rapidly, over hours. The Taum Sauk plant could deliver around 440 megawatts of electricity during peak demand, enough to supply hundreds of thousands of homes. The upper reservoir, sitting atop Proffit Mountain, was filled to the brim at night, then nearly drained by evening, with operators repeating the cycle to match the rhythm of the region's needs. The more water stored at the top, the more energy the plant could sell during those expensive peak hours. Every extra foot of water meant more revenue, but squeezing out that last bit of storage pushed the reservoir closer to its physical limits. With no traditional spillway to handle overflow, the plant depended entirely on sensors and controls to keep the water where it belonged. This invisible balancing act between profit and physical safety set the stage for what would come next. The upper reservoir at Taum Sauk sat on the summit of Proffit Mountain, encircled by a narrow rockfill embankment and lined with concrete. To squeeze out more storage, engineers added a parapet wall, just a few feet tall, on top of the embankment. This thin ring of concrete let the plant hold millions more gallons, but it also meant the difference between safe operation and disaster was razor thin. Over the decades, the parapet settled in places, dropping by nearly 2 feet in some sections. By 2005, the highest water line often sat just 1 or 2 feet below the lowest part of the wall. Unlike most dams, Taum Sauk had no spillway, no physical escape route for water if it ever rose too high. Everything depended on knowing the water level precisely. If the sensors were off, or if the system misread reality, there was nowhere for the excess to go but over the edge. The embankment was not designed to survive even a brief overflow. The rockfill beneath the parapet could be scoured away in minutes. Operating with such a slim margin left no room for error. Any mistake, whether from a faulty reading, a missed alarm, or a misjudged set point, could send water pouring over the crest. The entire safety net was invisible, woven from numbers on a screen and trust in automation. When the physical margin shrank to almost nothing, the system's fate rested on the reliability of its sensors and the judgment of those watching from miles away. At Taum Sauk, the physical safety of the reservoir depended almost entirely on its electronic nervous system. Instead of a concrete spillway or overflow channel, engineers installed a suite of sensors to monitor the water level. The main measurement came from pressure transducers mounted inside conduits that were strapped to steel cables running down the inner slope. These sensors converted water pressure into digital readings, feeding a programmable logic controller that started and stopped the massive pumps. Every fill cycle, operators in a remote control room relied on those numbers to decide when to halt pumping, trusting the sensors to reflect reality at the top of the mountain. As a backup, 2 conductivity probes known as Warrick probes were bolted to the parapet wall. Their only job was to act as an emergency cutoff, tripping the pumps if water ever reached a dangerous height. In theory, these probes provided an independent layer of protection, separate from the main pressure sensors. If both the transducers and the control logic failed, the Warrick system was supposed to stop the pumps before any water could overflow. After a major relining project in 2004, the setup changed. To avoid puncturing the new geomembrane, the sensor conduits were suspended from cables instead of being anchored directly to the wall. This made them more vulnerable to movement from daily filling and draining, and over time, the anchors loosened. The pressure sensors could shift, giving readings that no longer matched the true water level. Despite these mechanical risks, the plant continued to rely on automation, with the control room miles away and no routine physical checks at the reservoir itself. The entire operation became a closed loop of numbers, alarms, and trust in a system that was growing less reliable with each passing cycle. Inspection records from October 2005 show that Ameren's own staff found the reservoir's level sensing conduit loose and drifting out of position. The pressure sensors, meant to serve as the plant's eyes on the water, were giving readings that were lower than reality. That same month, operators documented water briefly overtopping the parapet wall, an unmistakable warning sign that the electronic safeguards were not catching dangerous conditions. Instead of shutting down the plant or physically repairing the sensor anchors, management chose a software solution. They reprogrammed the control system to stop the pumps when the sensors indicated the reservoir was 2 feet lower than the usual cutoff. This set point offset was a workaround, not a fix. Internal notes and maintenance logs reviewed by investigators show a pattern: known defects addressed with temporary measures, while the plant continued to operate at the edge of its limits. The real water level and the numbers on the screen were drifting further apart, but trust in the automated system remained. The vulnerability was now baked into daily operations, awaiting the next routine fill cycle. Shortly after 5 a.m., the control room's screens showed the reservoir still below its cutoff. In reality, water had already reached the lowest edge of the parapet. The pumps continued to run, driven by automation that trusted the sensors. On the mountain, a thin sheet of water began to spill over the settled rim. There were no warning lights, no urgent alarms, just the steady hum of machinery and numbers on a screen that lagged behind the truth. As the pumps forced more water into the reservoir, the overtopping deepened. The concrete parapet, never meant to resist flowing water, began to erode almost immediately. Chunks of concrete broke away, exposing the rockfill beneath. In less than 10 minutes, the overtopping carved a path through the embankment. The wall at panel 95 lost its footing and toppled outward. At that instant, the stored energy of 1 billion gallons of water was unleashed. The breach widened rapidly, and the upper reservoir began to empty down the mountainside. In the control room, the system finally registered a shutdown, but the collapse was already irreversible. Nearly 1.5 billion gallons of water surged through the breach, pouring down Proffit Mountain with a force few could imagine. The initial wave reached an estimated 150,000 cubic feet per second, comparable to the Mississippi River in flood, but unleashed all at once. In Johnson's shut-in state park, the flood rose to depths of 20 to 40 feet, stripping away trees, soil, and everything rooted to the ground. The superintendent's house, resting just above the riverbank, was swept off its foundation and carried a quarter-mile downstream. Inside, the superintendent's family, 2 adults and 3 children, were jolted awake by the roar and the violent rush of water. The house broke apart as it tumbled through the woods, scattering belongings and leaving the family battered but alive. Downstream, roads vanished, power lines collapsed, and the landscape was carved into new shapes. Yet, as the flood barreled into the lower reservoir, much of its destructive energy was finally absorbed. The surge that had the power to erase entire towns met its end in a basin designed to hold water, not disaster. Today, Nearly 80% of America's major dams rely on automated systems and human trust in them. As infrastructure grows more complex, silent failures remain the greatest risk. In a world built on code and sensors, safety demands vigilance, not faith. The next warning may not sound at all,